Hello friends, today we are going to talk about the electromagnetic waves. The information age in which we live is based almost entirely on the physics of electromagnetic waves. Like it or not, we are now globally connected by television, telephones and the web. And like it or not, we are constantly immersed in those signals because of television, radio and telephone transmitters. Much of this global interconnection of information processors was not imagined by even the most visionary engineers of 40 years ago. The challenge for today's engineers is to try and envision what the global interconnection will be like 40 years from now. The starting point in meeting that challenge is understanding the basic physics of electromagnetic waves, which come in so many different types and are studied under electromagnetic spectrum. The achievement of James Clerk Maxwell was to show that beam of light is the traveling wave of electric and magnetic fields, an electromagnetic wave, and thus that optics, the study of visible light, is a branch of electromagnetism. In this discussion, we move from one to the other. We conclude our discussion of strictly electrical and magnetic phenomena and we build a foundation for optics. In Maxwell's time, the visible, infrared, and ultraviolet forms of light were the only electromagnetic waves known. Encouraged by Maxwell's work, however, Heinrich Hertz discovered what we now call radio waves and verified that they move through the laboratory at the same speed as visible light, indicating that they have the same basic nature as visible light. As this figure shows, we now know a wide spectrum of electromagnetic waves. Consider the extent to which we are immersed in electromagnetic waves throughout this spectrum. The sun, whose radiations define the environment in which we as species have evolved and adapted, is the dominant source. We are also crisscrossed by radio and television signals, microwaves from radar systems and from telephone relay systems may reach us. There are electromagnetic waves from light bulbs, from the heated engine blocks of automobiles, from X-ray machines, from lightning flashes, and from buried radioactive materials. Beyond this, radiation reaches us from stars and other objects in our galaxy and from other galaxies. Electromagnetic waves also travel in the other direction. In the wavelength scale in figure and similarly the corresponding frequency scale, each scale marker represents a change in wavelength and correspondingly in frequency by a factor of 10. The scale is open-ended. The wavelengths of electromagnetic waves have no inherent upper or lower bound. Certain regions of the electromagnetic spectrum in figure are identified by familiar labels such as X-rays and radio waves. These labels denote roughly identified wavelength ranges within which certain kinds of sources and detectors of electromagnetic waves are in common use. Other regions of figure, such as those labeled TV channels and AM radio, represent specific wavelength bands assigned by law for certain commercial or other purposes. There are no gaps in the electromagnetic spectrum, and all electromagnetic waves, no matter where they lie in the spectrum, travel through free space, that is, vacuum, with the same speed c. The visible region of the spectrum is, of course, of particular interest to us. Figure shows the relative sensitivity of the human eye to light of various wavelengths. The center of the visible region is about 555 nanometer, which produces the sensation that we call yellow-green. The limit of this visible spectrum are not well defined because the eye sensitivity curve approaches the zero sensitivity line at both long and short wavelengths. If we take the limits arbitrarily as the wavelengths at which eye sensitivity has dropped to 1% of its maximum value, these limits are about 430 and 690 nanometer. However, the eye can detect electromagnetic waves somewhat beyond these limits if they are intense enough. Qualitative analysis of electromagnetic waves. Some electromagnetic waves, including X-rays, gamma rays, and visible light, are radiated, or we can say emitted, from sources that are of atomic or nuclear size, where quantum physics rules. But here we shall discuss how other electromagnetic waves are generated. To simplify matters, we restrict ourselves to that region of the spectrum in which the source of the radiation is both macroscopic and of manageable dimensions. The figure here shows, in broad outline, the generation of such waves. At its heart, it is an LC oscillator which establishes an angular frequency. Charges and currents in this circuit vary sinusoidally. An external source, possibly an AC generator, must be included to supply energy to compensate both for thermal losses in the circuit and for energy carried away by the radiated electromagnetic wave. The LC oscillator is coupled by a transformer and a transmission line to an antenna, which consists essentially of two thin solid conducting rods. Through this coupling, the sinusoidally varying current in the oscillator causes charge to oscillate sinusoidally along the rods of the antenna at the angular frequency of the LC oscillator. The current in the rods associated with this movement of charge also varies sinusoidally in magnitude and direction at angular frequency omega. The antenna has the effect of an electric dipole whose electric dipole moment varies sinusoidally in magnitude and direction along the antenna. Because the dipole moment varies in magnitude and direction, the electric field produced by the dipole varies in magnitude and direction. Also, because the current varies, the magnetic field produced by the current varies in magnitude and direction. However, the changes in the electric and magnetic fields do not happen everywhere instantaneously. Rather, the changes travel outward from the antenna at the speed of light c. Together, the changing fields from an electromagnetic wave that travels away from the antenna at speed c. The angular frequency of this wave is omega, the same as that of the LC oscillator. Electromagnetic wave. This figure shows how the electric field and the magnetic field change with time as one wavelength of the wave sweeps past the distance point P in the travelling wave as shown in LC oscillator earlier. In each part of this figure, the wave is travelling directly out of the page. The several key features are given here regardless of how the wave is created. The electric and magnetic fields are always perpendicular to the direction in which the wave is travelling. Thus, the wave is a transverse wave. The electric field is always perpendicular to the magnetic field. The cross product always gives the direction in which the wave travels. The fields always vary sinusoidally, just like the transverse wave. Moreover, the fields vary with the same frequency and in phase with each other. Looking at these features, we can assume that the electromagnetic wave is traveling towards P in the positive direction of an x-axis and that the electric field in is oscillating parallel to the y-axis and the magnetic field is then oscillating parallel to the z-axis. Then we can write the electric and magnetic fields as sinusoidal functions of position x and time t as E is equal to Em sine of kx minus omega t and B is equal to Bm sine of kx minus omega t. Here Em and Bm are the amplitudes of the fields and omega and k are the angular frequency and angular wave number of the wave respectively. From these equations, we note that not only do the two fields from the electromagnetic wave, but each also forms its own wave. Equation A gives the electric wave component of the electromagnetic wave and equation B gives the magnetic wave component. The two wave components cannot exist independently. Wave speed. We know that the speed of the wave is given by angular frequency divided by angular wave number, that is, speed is equal to omega upon k. However, because this is an electromagnetic wave, its speed in vacuum is given by the symbol c rather than v. In the quantitative analysis of traveling electromagnetic wave, you will see that c has a value equal to 1 upon under root of mu 0 into epsilon 0. In other words, all electromagnetic waves, including visible light, have the same speed c in vacuum. We will also see that the wave speed c and the amplitudes of the electric and magnetic fields are related by Em upon Bm is equal to c. Drawing the wave. We can represent the wave as in figure B, which shows the electric and magnetic field vectors in a snapshot of the wave at a certain instant. The curves through the tips of the vectors represent the sinusoidal oscillations given by equations A and B. The wave components of electric field and magnetic field are in phase, perpendicular to each other and perpendicular to the wave's direction of travel. Interpretation of figure B requires some care. The similar drawings for a transverse wave on a stretched string represented the up and down displacement of sections of the spring as the wave passed. There, something actually moves. Figure B is more abstract. At the instant shown, the electric and magnetic fields each have a certain magnitude and direction, but always perpendicular to the x-axis at each point along the x-axis. We choose to represent these vector quantities with a pair of arrows for each point, and so we must draw arrows of different lengths for different points, all directed away from the x-axis. However, the arrows represent field values only at points that are on the x-axis. Neither the arrows nor the sinusoidal curves represent a sideways motion of anything, nor do the arrows connect points on the x-axis with points off the axis. Quantitative analysis. Induced electric field. The dashed rectangle of dimensions dx and h in figure is fixed at point P on the x-axis and in the xy plane. As the electromagnetic wave moves rightward past the rectangle, the magnetic flux through the rectangle changes, and according to Faraday's law of induction, induced electric fields appear throughout the region of the rectangle. We take electric field and electric field plus differential element of electric field to be the induced fields along the two sides of the rectangle. These induced electric fields are in fact the electrical component of the electromagnetic wave. Note the small red portion of the magnetic field component curve for the y-axis. Let's consider the induced electric fields at the instant when this red portion of the magnetic component is passing through the rectangle. Just then, the magnetic field through the rectangle points in the positive z direction and is decreasing in magnitude. That is, the magnitude was greater just before the red section arrived. Because the magnetic field is decreasing, the magnetic flux through the rectangle is also decreasing. According to Faraday's law, the change in flux is opposed by induced electric fields, which produce a magnetic field in the positive z direction. According to Lenz's law, this in turn means that if we imagine the boundary of the rectangle to be a conducting loop, the counterclockwise induced current would have to appear in it. There is, of course, no conducting loop, but this analysis shows that the induced electric field vectors E and E plus dE are indeed oriented as shown in this figure, with the magnitude of E and E plus dE greater than that of E. Otherwise, the net induced electric field would not act counterclockwise around the rectangle. Let us now apply Faraday's law of induction counterclockwise around the rectangle. There is no contribution to the integral from the top or bottom of the rectangle because E and dE are perpendicular to each other. The integral then has the value E plus dE into h minus EH, which is equal to h dE. The flux through this rectangle is then phi b is equal to b into h dx, where b is the average magnitude of magnetic field within the rectangle and h dx is the area of the rectangle. Differentiating equation d with respect to t gives d phi b upon dt is equal to h dx into dB upon dt. If we substitute equation C and E into Faraday's law equation, we find h dE is equal to minus h dx into dB upon dt, which comes out to be dE upon dx is equal to minus dB upon dt. Actually, both B and E are functions of two variables, coordinate x and time t, as equation A and B show. However, in evaluating dE upon dx, we must assume that t is constant because this figure is an instantaneous snapshot. Also, in evaluating dB upon dt, we must assume that x is constant because we are dealing with the time rate of change of p at a particular place, that is the point P. The derivatives under these circumstances are partial derivatives, and equation F must be written as partial derivative of E with respect to x is equal to minus partial derivative of B with respect to t. The minus sign in this equation is appropriate and necessary because although magnitude E is increasing with x at the site of the rectangle in figure, magnitude B is decreasing with t. From equation A, we have partial derivative of E with respect to x equal to k Em cos of kx minus omega t, and from equation B, partial derivative of B with respect to t is equal to minus omega Bm into cos of kx minus omega t. Then equation G reduces to k Em cos of kx minus omega t is equal to omega Bm cos of kx minus omega t. The ratio of angular frequency and angular wave number for a travelling wave is its speed, which we are calling c. Then equation H becomes Em upon Bm is equal to c, which is the amplitude ratio of the electric and magnetic fields. Quantitative analysis. Induced magnetic field. Figure shows another dashed rectangle at point P in the transmitted wave. This one is in the xz plane. As the electromagnetic wave moves rightward past this new rectangle, the electric flux through the rectangle changes, and according to Maxwell's law of induction, induced magnetic fields appear throughout the region of the rectangle. These induced magnetic fields are, in fact, the magnetic component of the electromagnetic wave. We see from figure A that at the instant chosen for the magnetic field represented in figure B, marked in red on the magnetic component curve, the electric field through the rectangle of figure C is directed as shown. Recall that at the chosen instant, the magnetic field in figure B is decreasing. Because the two fields are in phase, the electric field in figure C must also be decreasing, and so must the electric flux through the rectangle. By applying the same reasoning we applied to figure B, we see that the changing flux will induce a magnetic field with vectors B and B plus dB oriented as shown in figure C, where field B plus dB is greater than field B. Let us apply Maxwell's law of induction by proceeding counterclockwise around the dashed rectangle of figure C. Only the long sides of the rectangle contribute to the integral because the dot product along the short sides is 0. Thus, we can write integral of b dot ds is equal to minus b plus db into h plus bh is equal to minus h dB. The flux through the rectangle is phi e is equal to E into h dx, where E is the average magnitude of electric field vector within the rectangle. Differentiating equation J with respect to t gives d phi E upon dt is equal to h dx into dE upon dt. If we substitute this and equation I into Maxwell's law, we find minus h dB is equal to mu 0 E 0 into h dx into dE upon dt. Or changing to partial derivative notation as we did earlier, minus partial derivative of b with respect to x is equal to mu 0 E 0 into partial derivative of E with respect to t. Again, the minus sign in this equation is necessary because although b is increasing with x at point P in the rectangle in figure C, E is decreasing with t. Evaluating equation K by using equations A and B leads to minus k Bm cos of kx minus omega t is equal to mu 0 E 0 into omega Em cos of kx minus omega t, which we can write as Em upon Bm is equal to 1 upon mu 0 E 0 into omega by k, which is equal to 1 upon mu 0 E 0 into c. Combining this with amplitude ratio equation leads at once to c is equal to 1 upon under root mu 0 into E 0, which is the wave speed. So friends, here we come to the end of our discussion in this lecture today, and therefore we sum up. An electromagnetic wave consists of oscillating electric and magnetic fields. The various possible frequencies of electromagnetic waves form a spectrum, a small part of which is visible light. An electromagnetic wave traveling along an x-axis has an electric field and a magnetic field with magnitudes that depend on x and t. So that is it for today. See you in the next lecture with more on electromagnetic waves. Thank you very much.